In this lesson, we will design a victim or stream buffer depth for strided, short loops to cut dead block evictions by 50%, and we will justify the choice both mathematically and graphically. First, the intuition. A dead block is a cache line that is fetched into the L1 cache, but gets evicted before any useful reuse, so it never yields a hit. Short loops with strided access can thrash a cache set, evicting lines before their next use. Here is a small set with associativity equal to 1, and a loop that touches 2 or 3 lines per set. Graphically, as the loop walks its stride, line L0 arrives and occupies the set. Then line L1 arrives and evicts L0 before any reuse. Then line L2 arrives and evicts L1. When we come back to L0, it is gone. Every access is a miss. That is a dead-on fill pattern. Now, the model. We define S as the number of cache sets, S as the stride measured in cache lines, and L as the number of unique cache lines touched by the short loop footprint. The loop touches K, distinct sets, where K equals S divided by the greatest common divisor of S and S. The per set working set is uneven but tightly bounded. W low equals the floor of L over K, and W high equals the ceiling of L over K. Finally, A is the associativity of the L1 cache. Baseline dead block behavior is set thrashing. If W low is greater than A, then every access is dead on fill, and the dead block fraction is 1. If W low is less than or equal to A, but W high is greater than A, only the high sets thrash. The number of high sets is N high equal to L modulo K. A victim buffer behaves like extra associativity per set because it can hold recently evicted lines long enough to serve their next use. Let V be the effective depth per set contributed by the victim buffer. The effective associativity is a plus V. A clean way to get a 50% reduction is to choose V, so that W low is less than or equal to a plus V, but W high is still larger than a plus V. That way, only high sets keep thrashing. Then the dead block fraction becomes the share of accesses in high sets. Under this construction, we can make the algebra crisp. If we start from a worst-case baseline with W low greater than A, the baseline dead block fraction is 1. After we add V that just fixes the low sets, but not the high sets, the new dead block fraction, F1, is the fraction of accesses in high sets. Setting F1 equal to 1/2 yields a direct relation between the number of high sets and K. Let us pick a small, visual-friendly example. Take K equals 10 sets touched by the stride pattern, and choose working set per set W low equals 2 and W high equals 3. So N high sets carry 3 lines, and the rest carry 2 lines. Set A equals 1, and choose V equals 1. Then A plus V equals 2. This satisfies W low less than or equal to 2 less than W high. Our formula predicts that N high equals 2/5 of K, which is 4. The loop touches L equals 10 times 2 plus 4 equals 24 lines. Baseline F0 is 1, and the new F1 equals 4 times 3 over 24 equals 1/2, exactly 50% reduction. Now a bar picture. Each bar shows how many distinct lines map to a particular set within one loop footprint. The blue horizontal line is the associativity A equals 1, and the green line is a plus V equals 2. Bars at height 2 are fully covered by the victim buffer. Bars at height 3 still thrash. They account for exactly half of all dead block evictions in steady state. The victim buffer depth you need per set is the gap between the low working set and associativity. V equals W low minus A clamped at 0. This ensures low sets stop thrashing, while high sets may still thrash. That is exactly our 50% construction. A stream buffer variant aims to bypass dead-on fill lines from L1 and hold them until use. The excess beyond associativity per set is about W low minus A for most sets. Holding about 1/2 of that excess per set yields roughly 1/2 fewer dead block evictions. A practical formula is P equals the ceiling of 1/2 times the positive part of W low minus A. In our example, W low minus A equals 1, so P equals 1 entry per set. Quantitative summary. Example parameters. K equals 10, W low equals 2, W high equals 3, A equals 1. Choose victim depth V equals 1, or a stream buffer depth of P equals 1 per set. Baseline dead block fraction F0 equals 1. After adding the buffer, F1 equals 1/2. Reduction equals 50%. The bar picture showed that only the 4 high sets still thrash, which account for exactly half the accesses. Key concepts. 1. Reuse distance driven by the number of distinct lines per set. 2. Victim depth acts like extra associativity. 3. To get a 50% reduction cleanly, lift low sets just to capacity, but leave high sets barely above capacity. 4. An equivalent stream buffer keeps about half of the excess beyond associativity per set. That is how to design and justify a buffer depth for strided short loops that has dead block evictions, with both a mathematical derivation and a clear graphical picture.